In this video, we're going to take a look at simplifying radical expressions, and in particular, we're going to look at how to use the product rule and quotient rule for radicals. All right, so let's get started. It says the product rule for radicals. If you have the nth root of a and the nth root of b, and they're both real numbers, then the nth root of a times the nth root of b equals the nth root of ab. So if you have two separate radicals, you can combine them as long as their indexes are the same. You can combine them into one radical. And that also works in reverse. If you have one radical, the nth root of a times b, you can split them up into two different radicals. This is really handy for reducing radicals. This is really handy for combining radicals. Alrighty, so let's get started. Let's use the first rule. We have two radicals, they're being multiplied. They are both square roots, so we can do that multiplication under the radical, 5 times 7, to get the square root of 35. All right, how about for the second example? We have two radicals, they're both square roots, they're being multiplied. Again, they have to be multiplied in order to use the product rule. We'll combine them both into a square root and multiply them to get the square root of 13z. So I'm going to move down here to a cube root. They're both cube roots and they're being multiplied. So really all I'm going to do is do the multiplication of the cube root under the root. 5 times 3 is 15. X squared y. And the last one I'm going to do before we do the fourth root one is another square root. They're fractions. So because they're both square roots, right, they both have the same index, I'm going to do that multiplication under the radical. So remember, when we multiply fractions, we multiply across. So it's 5t over 2m. All right, so really, once we combine these into one radical and get our answer, we really should be looking to see if we can simplify it. But I know that 35, the only factors of 35 for our first example here, are 5 and 7, so that doesn't simplify. 13's prime, so that doesn't simplify. And then we have the cube root. 15 is the only factors are 3 and 5, so that doesn't simplify. And we only have two x's here, so we can't simplify our variables. And same with the variables in our second example and our last example. They don't simplify because I don't have two of any of our variables. So now let's take a look at this last example here. This is the fourth root of 125 times the fourth root of 5. So we can combine that under one radical, that product under one radical, and instead of actually multiplying, I'm going to look to see if it simplifies first. I knew the other ones didn't simplify because I know a lot about the number 35, 15, 13, and 5. But what about this number here? Let's go ahead and factor 125. I know 125 is 5 times 25, and I still can't forget this 5 over here. And then I know that 25 is 5 times 5 times 5 times 5. And now I know I can actually simplify this. I have a group of 4 5s, and so when I simplify this, I get the answer of 5. So if I had just multiplied this out, this would be the fourth root of 625, which I would then have to factor, and I would still get 5 times 5 times 5 times 5. So if I'm unsure, I typically don't do the multiplication first. I check to see if I have factors, because it's easier to factor 125 than it is to factor 625. All right, so let's move on to the quotient rule. So the quotient rule here says that if the nth root of a and the nth root of b are real numbers and the nth root of b is not 0, then we can combine the quotient of these two radicals. So the nth root of a over the nth root of b equals the nth root of a over b. And also it works in reverse. The nth root of a over b, we can split that up into two different radicals, into the nth root of a over the nth root of b. So we're going to use the quotient rule, and we're going to use the quotient rule in this direction first. We're going to split it up. So to find the square root of 36, we simply have to split our radical up. You guys probably already know the answer without splitting it up. But we can split it up by using the quotient rule and get 6 over 7. We can do the same here for our next example. We can split it up, the square root of z over the square root of 16, which is just the square root of z. It does not simplify. We don't have a group of 2 z's over 4. And now we can do the same with cube roots and fourth roots. So when we do this example here, we get the cube root of 125 over the cube root of 8, which is just 5 over 2. And our last example here, we get the fourth root of 5 over the fourth root of 81x to the 8th. So our final answer for this one is going to be the fourth root of 5 over, I know that 81, if we go and we factor 81, we get 9 times 9, and then we get 3 times 3 times 3 times 3. We're looking at the fourth root, so we're looking for groups of 4. I'm going to pull one of those threes out. And then when we take a look at the fourth root of x to the 8th, how many groups of 4 are in 8? Well, we have 2 groups of 4 in 8. So we get x squared. So this is the final reduced answer. Okay, the next topic I want to talk about is strategies for simplifying radical expressions that contain variables and numbers and expressions where maybe it's not a perfect square or a perfect cube or a perfect power of n. All right, so that we can't simplify the radical away, we're going to have a radical in our answer. Well, there are a couple of ways that we can do that. And I have outlined 3 strategies right here. First off, here's an example right here, the cube root of 27x to the 6th. This one actually simplifies all the way where your radical reduces out, but there are 3 methods to do this. The first method is you could think what could be raised to the power of the index n to get the radicand. So in this case, what could we raise to the power of 3 to get 27x to the 6th? So I make parentheses with a power of 3 on the outside, and I know that 3 cubed is 27, so I put 3 in here. I know that x squared cubed raised to the power of 3 is x to the 6th, because remember I multiply our exponents here. So I know that 3x squared quantity cubed equals 27x to the 6th. So the cube root of 27x to the 6th is going to be 3x squared. I can also write each factor in terms of its prime factors. And then look for groups of n. And this is similar to how you guys factored numbers last year. You made factor trees. So I know that 27 is 3 times 3 times 3. And x to the 6th is x times x times x times x times x times x. Right, when I go and circle groups of 3, I take 1 out from each group that I've circled. So I pull out 1, 3, I pull out 1x, and then I pull out another x to get 3x squared. All right, so what's the next strategy that you could use? Well, you could write the coefficient in terms of powers of its prime factors, then divide all exponents by the index to calculate the value of the radicand. So again, we would have to factor 27 into 3 cubed, and then the x to the 6 stays the same. So what we could do here is we could see how many groups of 3 go into 3, and how many groups of 3 go into 6, and use that to get our answer. So I have one group of 3 in 3, so 3 divided by 3 is 1, so I pull out 1, 3. Right, so then I have 6 divided by 3 is 2, so I pull out 2 x's. All right, so we can use those strategies, but I'm also going to walk through another strategy. So I also like to take a look at simplifying by finding out, for instance, a square root. What is the largest perfect square that is a factor of 98? Or maybe what is the largest perfect cube that is a factor of 54? Or the largest perfect square that is a factor of 35? Or the largest perfect power of 4 that is a factor of 243? So I'm going to do these in a couple of ways. So for the first one, I'm going to take a look at 49 and squares. I know that 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And let's see, 4 doesn't go into 98, 9 doesn't go into 98, 16 doesn't go into 98, 5 squared is 25, 25 doesn't go into 98, 6 squared is 36, and I know 36 doesn't go into 98, but then I get to 7 squared, 49. 49 does go into 98, and it goes into 98 twice. So 49 times 2 is 98. I know that I can use my product property and separate these into 2 square roots, and I know the square root of 49 is 7 square root of 2. So this is really my final answer. The other way that I could do this is I could say the square root of 98, and I could go through my factor tree. 2 times 49, 7 times 7, and I can circle a group of 2 and pull 1 7 out. Any number that isn't in my circle that is a leaf of this factor tree stays under the radical. So either way that I decide to do it, I get the same answer. All right, how about the cube root of 54? Well, what are perfect cubes? Let's go down our list of perfect cubes. I'm going to write them across the bottom here. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. Well, look, I know that 27 goes into 54 twice. How about if we did 4 cubed? That's 64. A little bit too big, right? We can't put 64 into 54. So I'm going to rewrite 54 as 27 times 2. And then I'm going to use my product property to separate this out into the product of 2 different cube roots. I know that the cube root of 27 is 3. So my final answer is 3 cube root of 2. And again, I could go ahead and use my factor tree and go 2 times 27. 27 is 3 times 9. 9 is 3 times 3. I have my group of 3 3s here, so I'll pull 1 out. And here's my only number that's a leaf that is not in a group, so it stays under the radical. So how about the square root of 35? Well, I know 35, I don't know any perfect squares that go into 35. 1 doesn't, well, 1 does, but we're looking for numbers bigger. 4 doesn't, 9 doesn't, 16 doesn't, 25 doesn't, and 36 is too big. So just to check this out, the only prime factors that go into 35 are 5 and 7. I have no groups of 2, so the square root of 35 is as simple as it gets. So how about the 4th root of 243? So how about powers of 4? Let's look at powers of 4. 1 to the 4th is 1. 2 to the 4th is 16. 3 to the 4th is 81. 81 goes into 243 3 times. Let's see, how about 4 to the 4th? Well, that's 16 times 16, that's 256. Too big. So this is the largest power of 4 that goes into 243. So I have 81 times 3 is 243. So I'm going to use my product property and split this up into 2 radicals. And here the 4th root of 81 I know is 3 4th root of 3. Final answer for this one. I can also break this down into 3 times 81. which is 9 times 9, which is 3 times 3 times 3.